Hi, ladies and gentlemen. We're going to be talking today about strength of covalent bonds. This is a section in your textbook. This is section 8.8. So I highly recommend that you read section 8.8 in a white textbook. I recommend that you look at the sample problems in section 8.8. I recommend that you work the sample problems in section 8.8 so you really have a good understanding of what's going on here, because you never know when there might be a quiz thrown at you about section 8.8. We're going to be talking about bond enthalpy today, and to give you the definition of what we're talking about. This is going to be the energy required, which is often given as delta H. Once again, enthalpy meaning heat at a constant pressure. This is going to be the energy required to break a mole of bonds in gas molecules. So what we're doing is we're breaking bonds, and then we're going to be forming bonds. And I'll give you a real quick example of what we're talking about here. Is, let's say if we have diatomic chlorine gas. If we were to draw the Lewis dot structure of diatomic chlorine gas, we would have two chlorine molecules bonded together just like this. They'd have a single bond in between them. They'd be a covalent bond. And if we want to break these bonds, we have a single chlorine-chlorine bond that is shown right here, just a single bond shown right there. And we're going to break these guys up into just a chlorine atom with it's one valence electron, and of course we're going to have two of these guys. That is what we're talking about here, is just breaking up that single bond. Okay. Now, bond enthalpy, this is a good note that we need to take care of, is going to be always positive. It takes energy. It takes energy to break bonds, and it also gives off energy or releases energy many times to make bonds, and we'll be talking about that here in a little bit. Now, some of the problems that we're going to be doing for tonight's homework, these problems are going to require you to look up some average bond enthalpies. So in page 330 of your white book is a table that looks just like this. You don't need to copy this down. You'll always be given these values or asked to calculate these values depending. And so let's just kind of look at these guys. So if we have a single bond, a single carbon-hydrogen bond, for a mole of these guys, it's going to take 413 kilojoules per mole just to break that. And so it goes all the way down. You've got all these different types of bonds. You notice that a silicon-oxygen bond is pretty strong as well, 368, things like that. Okay, so we can find whatever we need in here. You'll also notice, and here's something pretty interesting, is you'll notice in these double bonds, it takes a little bit more energy to break a double bond, and it takes even more energy to break a triple bond. And so just to highlight a couple of those, right up here at the top on the single carbon-carbon bond, 348 on average, and coming down here to the multiple bonds, it takes 614 to break a double-double carbon bond, and then down here for a triple bond, it's 839. So it takes more energy to break a triple bond than it does a single bond, but it's not necessarily, how should we say, it's not necessarily a perfect, if we graphed it, it wouldn't be a perfect straight line. It's not linear, not a direct relationship. Talk more about that later. Okay. Let's go down here a little bit more and talk about a formula that we're going to use when we're asked to calculate this stuff in particular. So here's the formula that we're going to use. And the formula is delta H reaction. We might be asked to calculate delta H of reaction. And it's the sum. It looks like for some reason it cut something off down there. That's the word sum. That's not what I want to have happen. And I just cut more stuff off. There, it's back. It's a miracle. Okay, so basically what we're dealing with in this formula is the sum of bond enthalpies of bonds broken minus bond enthalpies of bonds formed. And of course, it's the sum. Now, this formula might seem familiar. We worked with a formula before that was products minus reactants when we were calculating delta H values. This one is bonds broken, and the reactants are going to be broken, and the products are going to be what's formed. So we got to keep those straight, especially when it comes time for the AP test. Bonds broken are reactants, bonds formed are products. When we calculated different delta H, it was the other way around. So we just got to keep that in mind. Here's an example that we're going to do, and I'm going to ask you to calculate, using this formula, delta H of reaction bonds broken minus bonds formed. And here's the example. We're going to use N2H4 decomposes into N2 and H2 gas. Now, the first thing that we're going to want to do in this type of problem is we need to draw the Lewis structures of each one of these, just so we know what kind of bonds we're dealing with. And the N2H4, we're going to have a nitrogen single bonded to a nitrogen as our central atoms. We're then going to have a hydrogen single bonded, and single bond hydrogen, another single bond hydrogen, just like that. Okay, I'm also going to throw on an unshared pair of electrons on each one of these nitrogens, although it's not really going to come into play here for us. And so then we go like that, and then we're going to form N2, diatomic nitrogen gas. Diatomic nitrogen gas forms a triple bond, unshared pair of electrons, and then we have H2, which forms a single bond. Okay, so what we need to do is we need to figure out how many of these bonds are being broken and how many bonds are being formed, and we're going to go back and we can do this calculation. So let's just first off talk about that. And so first thing is we're going to have some hydrogen-nitrogen bonds, and we have 1, 2, 3, 4 of these guys that we're going to look up the values for in a minute. We're going to add that to a nitrogen single bond, which is right here. And so we've taken care of all the bonds. And that is all going to be added together. And we're going to subtract it from a single triple nitrogen bond. That's a triple bond. And we're going to add that to a single hydrogen bond. So now we're going to go look these values up and see what we get. So the first thing is we're going to look up the value, and we're going to multiply it by 4, whatever that value is. It's going to be the hydrogen-nitrogen bond. So I'm looking at the table. I'm not going to scroll up there. I found a nitrogen-hydrogen, hydrogen-nitrogen, same thing. It's 391. Okay. And then we're going to add that into a single nitrogen-nitrogen, which is 163. We're going to subtract out. We're going to make a triple. We're going to make a triple nitrogen-nitrogen, which is 941. And we're going to make a single hydrogen-hydrogen, which if I look it up at 436. Okay, now I just noticed I made a mistake here, so I've got to correct this mistake because this is a huge mistake. One of the mistakes I did make is I forgot to balance this equation. And so if I go back up to the top here, and I have N2H4, over on the product side I have 2 N's, okay, so I need a Roman numeral 2 right there. And so what that's going to do is that's going to change this number here, so you're going to have 2 hydrogens. It's also going to change that number there. So you're going to multiply 2 through right there. Okay? So we did have to balance this equation first. So when I run this all the way through my calculator, bonds broken minus bonds formed, I came up with a value of negative 86 kilojoules per mole as my answer. So this guy is going to be giving off some heat when we make this reaction. Okay, so that's all we have to do is make sure we go through and get all the bonds, do our calculation, and then follow the formula. The last thing I want to talk about for today's lecture is bond enthalpy and bond length and sort of their relationship. And we'll use carbon as an example. And we talked about this before. If we have a carbon-carbon single bond, the measurements in carbon-carbon single bond on average run about 1.54 angstroms. Very small. The value to break this bond would be 348 kilojoules per mole. Okay, so if we have a carbon-carbon double bond, the length is 1.34 angstroms, and the value is 614 kilojoules per mole. And then if we have a carbon-carbon triple bond, its length is 1.20 angstroms and 839 kilojoules per mole. And so let's go over here and put delta H value and bond length. Okay. So really what this says is, as we said before, single bonds are basically the longest, and they're the easiest to break. They require less energy, whereas a triple bond is the shortest and requires more energy to break. And that's all really we're going to say about that. We can relate those things all together. So there will be some problems that go not along with tonight's homework. Hope you guys have a great evening.